Well, here we are in the real world, and I hate to tell you, but things don't always work out the way they should. In particular, stoichiometry may tell us that we should make 100 grams of this product, given the amount of reactant that we started with, and we do the reaction and we don't get 100 grams. We get 30 grams, or 20 grams, or sometimes even less. Why in the world would that happen? Why would we ever get less than stoichiometry predicts that we ought to get? Well, there's several reasons. One reason, and one that's under our control, is bad lab technique. Maybe we spill a little bit as we're working, or maybe we have to move our product from one container into another, and we don't get quite all of it out. Or there's just any number of things that we could do wrong that would cause us to get less of our product than we expect to get. Another possibility, and there's nothing we can do about this one, is the reaction we're working with may be a reversible reaction. The reactants form products, but then the products turn around and form reactants again. And so you don't wind up with as much product as you expect because it formed more reactant. That's kind of crazy. All right, so reversible reactions. And another reason that we really can't do much about is that as our reaction proceeds and we get more and more product, it may be hard for the reactants to bump into each other. For instance, maybe at the beginning of our reaction, we have A's and B's all over the place. And so it's very easy for an A to bump into a B and form whatever the product is. But as our reaction proceeds, that is no longer true. Most of our A's and B's have bumped into one another and reacted. They formed AB. But we have a little bit of A way over here and a little bit of B way over here. What are the chances of them bumping into each other? Not too good. As B heads over, it's going to hit an AB and bounce off. As A heads for B, it's going to hit an AB and bounce off. So it may just be that they never happen to run into each other. And there's not much we can do about that. They just don't collide. So, facing that fact, sometimes we need to know what percent did we get of the amount we should have gotten. And this really is as simple a calculation as you think it ought to be. Let's do an example. Alright, if I react 16 grams of potassium with water and get half a gram, I better put another significant zero in there, of hydrogen, what's my percent yield? Is that good or is that bad? Well, just like with any other stoichiometry problem, the first thing we've got to do is write the balanced chemical equation. So we know that potassium and water will be the reactants. We know that hydrogen will be one product, but it certainly is not going to be the other product. What happened to the potassium? What happened to the oxygen? Well, this is a single replacement reaction. The potassium is going to kick the hydrogen out of the compound and grab the hydroxide for itself. And so here's our potassium hydroxide. That's our other product. Now, is it balanced? One potassium, one hydrogen that is not hydroxide, two hydrogens that are not hydroxide. So we're going to have to increase the side that doesn't have enough. That gives me two hydroxides, one hydroxide. But that gives me two potassiums. Now I'm balanced. All right, let's label the amounts. I know I started off with 16 grams of potassium, and I wound up with half a gram of hydrogen. Tempting to put it there, but really what I want to know is how much hydrogen should I have gotten? So let's make that our question. That means that since we know potassium, we'll call potassium A, and we'll call hydrogen, which is what we want to know, B. So we start into the map, and we start with our 16 grams of A. All right, 39.1 grams of A is the same thing as 1 mole of A. That gets us out of mass of A. Looking at the balanced chemical equation, we see that we'll get 1 mole of B every time we use up 2 moles of A. Right, that will get us out of moles of A. And then we want to get out of moles of B and into grams of B, because that's what we have to compare it to. And hydrogen being diatomic, 1 hydrogen atom would be 1, 2 hydrogen atoms will be 2. And that will get us out of moles of B. So now we grab our handy dandy calculator and we say 16 divided by 39.1 divided by 2 times 2, well, we could have skipped those last 2 steps, is going to give us, oh, we've got 2 sig figs, 0.41. So the most that we could have gotten in a perfect world would have been 0.41 grams of hydrogen. Well, this is the danger of making up your own problem, because I said we got more than was actually possible. And sometimes that happens in the real world. Generally means that your product is impure as heck. And so you're getting the mass of your product plus your mass of some kind of grunge that you did not adequately separate before you started trying to find your mass. So let's change this to 0.25 grams. See, that's the luxury that I have as a teacher. I can go back and change the problem. You can't do that. Alright, so if I got 0.25 grams and I should have gotten 0.41 grams, what percentage is that? Well, that's easy. 0.25 grams divided by 0.41 grams. My grams will cancel. Multiply by 100 to change it into a percent. And I find that my percent yield is 0.25 divided by 0.41 times 100 will be 60.9 with 2 sig figs, be about 61% yield. Now, is that good or bad? It depends. There are reactions where that would be stinking dog awful. There are reactions where that would be thrillingly wonderful and you would write a paper about it and publish it and become famous and wealthy. It depends on the reaction. For this one, that's pretty bad. But, you know, capturing the hydrogen gas is a little tricky. Alright, so this is very straightforward. You just do the stoichiometry and then you do a common old middle school percent. We can do this.